Okay, let's start now. So my subject today is this one, universal enveloping algebras, and PBW, which means Poincaré-Birkhoff-Witt. And the next topic will be the center of the universal enveloping algebra. And the center is something which is very important for representation theory. This is the reason why I would like to develop this concept. So let's begin by some generalities. I'm sorry, just... Okay, so fix a vector space V. And I recall the notion related to the tensor algebra. So this is my notation for the tensor algebra. This is a graded algebra, which is composed from the tensor powers of different degree of our space. And associated to it is the symmetric algebra. Of course, this is well known, but I would like to repeat this just to be sure that all is complete. So this is the symmetric algebra. It is defined as the quotient of a tensor algebra by the two-sided ideal, which is generated by all elements of this form, where x1 and x2 are arbitrary elements of V. So I use here the fact that this space is indeed an associative algebra. And this is the symmetric algebra, and because of a very definition, it's a commutative algebra. So this object is non-commutative, and this object is commutative. Next, what is important for us is the following fact. If V is finite dimensional, then we have a canonical identification of our algebra, the symmetric algebra of V, with the algebra of polynomials on the dual space. So this is V star is my notation for the dual space. Now I recall very briefly what I need for Lie algebras. So I assume that this Gothic G is a Lie algebra, which means that there is a binary multiple operation, the map from G cross G to G, which is skew-symmetric and satisfies this identity, which is called the Jacobi identity. And the basic example is the following. Take an arbitrary associative algebra, A, and turn it into a Lie algebra by proclaiming the bracket between two elements x and y as the commutator. Then all the necessary conditions will be satisfied because this operation is skew-symmetric and satisfies the Jacobi identity, which is easily verified. And now the definition of a universal enveloping algebra. So assume that G is again some Lie algebra, and the universal enveloping algebra is an associative algebra, which is defined as follows. Take the tensor algebra of a vector space G, so here we don't need any additional structure. But now we use the bracket as follows. We take the two-sided ideal, which is generated by all elements of this type, xy minus yx minus the bracket between x and y. Okay, so this is a formal definition. So it means that It means that in this algebra, you always have the following identity. We have it x, y minus yx equals where x and y are arbitrary elements of our initial Lie algebra. So we want to have this relation. So this is our motivation for introducing this object. Okay, so we have a canonical map, and by this property, you have that this map is a morphism of Lie algebras if this associative algebra is equipped with the Lie algebra structure, which comes from the commutator. This just follows from this fact. And it's universal because the following universality property holds. So given an arbitrary Lie algebra morphism from our algebra G to some associative algebra A, there exists a unique algebra morphism from this object to this one, such that this diagram is commutative. So this is the initial data, this is the canonical map, and the property is there exists this row, and moreover, it's unique. Okay? So this is easily seen from a very definition that our construction produces the object with the desired property. What next? It's very important for us that our object U of G is a filtered algebra. This means that there is a chain of growing subspaces. I use this notation. So this object is the subspace of dimension less or equal to n. And the definition is that this subspace is spanned by arbitrary monomials of length at most n. And I use this symbol, this circle, to denote the multiplication in the universal enveloping algebra, to distinguish it from other multiplication, which you will see why it's convenient. So this is the multiplication in the universal enveloping algebra, which is inherited from the multiplication in the tensor algebra. Okay, so it's verified that it is indeed a filtered algebra. What means a filtered algebra? This means that if you take two elements, say A of degree, say less or equal to K, and some other element B of degree less or equal to L, then the product has degree less or equal to K plus L. So this just means that this structure, this filtration, is compatible with multiplication. So this is very important for us to have this property. And it enables us to introduce the associated graded algebra. This is a general definition which makes sense for an arbitrary filtered algebra, but how to do this? How to define the associative graded algebra? As follows. So we have to prove the property that if you have an element of degree at most k, another element of degree at most L, then the commutator has degree strictly less than k plus L. And then we can define, I forgot to define it. So this object is defined as follows. In this algebra, the homogeneous component of degree n is, by definition, the quotient of this subspace modulo this subspace. So this is a general definition which works for any filtered algebra. So for any filtered algebra, we can replace U of G by any filtered algebra. This definition gives us a graded algebra. And the grading will be compatible with multiplication, meaning that the product of two homogeneous elements has degree equal to the sum of their degrees. But here the claim is that the graded algebra constructed according to this general definition is commutative. So this property just says us that it is commutative because modulo the lower degree term, we get here 0, modulo this subspace which has smaller degree. So we have to prove this. How to prove this? This is easy. Just use the definition. So take by linearity, we may assume that our A has this form, some monomial, and B is some another monomial, and the letters are elements of the Lie algebra, and simply use induction on K or on L, and the simple rule which holds for an arbitrary associative algebra. If you take a commutator between some product and some other elements, we can apply this rule. And using this, it is easy to see by induction that we have this property. We have this desired property. So, as a corollary, we have that we produced some commutative algebra. And the corollary is as follows. We have a canonical morphism of associative algebras, which are commutative, which are both commutative, from this algebra to this algebra. Because the definition, if you compare the definition of this object as a factor or as a quotient of the tensor algebra, and this two-step definition. First, we defined this as some quotient of a tensor algebra, and then apply this operation by taking the associative graded algebra. Comparing these two definitions, we see that we have a canonical morphism from this to this one, which is just defined by the fact that an element of the Lie algebra are mapped to themselves. So this is trivial. This is absolutely trivial. But what is non-trivial? Non-trivial, so the trivial claim is that this map is surjective. This is trivial because this and these objects are generated by the Lie algebra elements. What is non-trivial? Non-trivial is the PBW theorem, which says that this is in fact an injective map and hence is an isomorphism. This seems to be also evident, but it's not. It's not. And it requires some proof which is not at all trivial. In the case of real Lie algebras, one can identify the Lie algebra in the case, let me write this, maybe it's better in the case of real Lie algebra, G, which we assume to be the Lie algebra of some Lie group. One can realize our Lie algebra as the algebra of left invariant vector fields on the Lie group, and then we get that the claim is more or less equivalent to the following: to that U of G is the algebra of left invariant differential operator on G. It seems what is called the Laurent-Schwarz theorem. And from this fact, one can prove, this gives us some tool for proving the Poincaré-Bergefell theorem in this particular case. But in fact, this result holds without restriction to be that the ground field is a field of real numbers. It's a very general fact. It can be found in any good textbooks about representations or Lie theory. I don't want to prove it. And here is an equivalent formulation. It is as follows. So pick an arbitrary basis in our algebra. Here I assume that it is finite dimensional, but it's not important in fact. And the PW theorem holds without this restriction. So here again, also one can take an arbitrary basis, abstract basis in an abstract Lie algebra of any dimension. Okay, so assume it's finite dimensional for brevity. Then the ordered monomials. Ordered means that we consider only monomials in the universal enveloping algebra, where the indices are weakly decreasing. So it's enough to take these monomials and we get in, and then together with the unity, they form a basis, a linear basis of our associative algebra. So this means that any element of this algebra can be written as a finite linear combination of the ordered monomials. Sorry, what happens here? Okay. So for instance, to get the flavor of this fact, so assume that we have two elements and we want to reorder them. So we want to write plus something, but it's possible because this simply means that and this is another element of Lie algebra. So using this simple rule, we can reorder in any way we wish any monomial and reorder the terms, reorder the letters in any order. Now, I want to define the so-called symmetrization map. So the meaning, some informal meaning of the PBW theorem is that these algebras, this commutative algebra, the symmetric algebra, and non-commutative algebra, in the first approximation, they are similar. Informally, they are of the same size. And because of this, but I would like to stress that this algebra is always commutative, and this algebra is typically non-commutative unless the Lie algebra is abelian. So the structures are different, but they are close to each other. And this informal claim is very important. We want to compare this object and try to reduce some claims regarding this algebra to some similar claims regarding the symmetric algebra. This is some common theme of many areas in representation theory and in Lie theory. So what is the symmetrization map? The claim is the following. There exists a unique linear isomorphism, not an algebra isomorphism, but only isomorphism of vector spaces, which I will denote by the symbol, between the symmetric algebra and the universal enveloping algebra, which is characterized by the property that for any element of Lie algebra, it's the image of the nth power of this element is equal to the nth power, but with respect to multiplication in this algebra. So all this seems to be trivial, but let's think a little bit what this means. So this is the symmetrization map. Why symmetrization map? Let's regard in more detail what happens. Take arbitrary elements of our Lie algebra, take arbitrary scalars from the base field, and substitute for x this linear combination, and look what happens. Look what happens. On the left and on the right, we get some polynomials in these variables, in the lambdas. We fix the x's and we get something which are polynomials with respect to these scalars. And take the term which is equal to the product of a lambda. So this is related to well-known trick in algebra, in linear algebra, which is called polarization. And this gives us the following. Sorry. This gives us the following. The image under our map of this monomial is equal to the symmetrization in the universal enveloping algebra. So we take arbitrary permutation, we permute these letters in any possible way, and to compensate, divide by the n factorial. We can transfer this factor on the left, and then we get exactly the equality of the coefficients corresponding to the product of the lambdas. So this is just the consequence of this comparison. And this argument shows that if a symmetrization map exists, then it is unique, because this property just says us how to define our map for any monomial. And conversely, what happens here? Don't understand. Sorry. So conversely, so pick a basis now, and use this equation, this relation, to define our map on the basis element. And this gives us the existence. So this is the end of the proof. Now the properties of the symmetrization map. So I repeat, it's not an algebra isomorphism unless G is commutative, but it is, in the first approximation, it is. So if you take the image under symmetrization of the product of some two elements A and B, we get the product of the images up to low degree terms. And a reformulation of this property. Suppose that we have some elements of Lie algebra and the symmetrization is equal to these elements up to lower degree terms. So this is an example. Don't understand what happens. Here is an example. The image of a product of two elements is equal to this one, which can be written in this form. And some elements of lower degree. This element has degree 2, and this one is of degree 1. The next fact. So assume we want to consider the automorphism group of our Lie algebra. So it is formed by element in the group of all invertible operators on the vector space G, which preserve the structure, the bracket of the Lie algebra. So this is the automorphism group. And this group operates. It is a group of symmetry. So it operates everywhere. It operates on the symmetric algebra, and it operates on this algebra just because it is a symmetric group. It is something which preserves all the relevant structures which we need. And the claim is that this map, I mean the symmetrization map, is equivalent with respect to the action of the automorphism. Don't understand what. Excuse me. So the proof is obvious. This is trivial. The related claim. So here I assume that the ground field is the field of real of complex numbers. So assume that G is a connected, it's very important here, it's connected Lie group with Lie algebra equal to our initial Lie algebra. Then we have the result which is called Gelfand theorem. It says that the symmetrization map between our symmetric algebra and the universal envelope algebra induces a linear isomorphism of the algebra, of a subalgebra of invariance with respect to the action of our Lie group, and invariance here. But because the group G is connected, the invariance, the G invariance in the universal envelope algebra are the same as the center of this non-commutative algebra. And the center is just the object we are interested in. So actually, I want to understand the structure to get some information about the center. This is a natural question because the algebra is not commutative. So maybe the first question is, what is its center? And the idea is that one can use the symmetrization map for extracting some information about the center from the structure of this object. And this object is much easier to understand, the algebra of G invariant in the symmetric algebra. So first, let's prove why it's called true. The idea is that, so here I just wrote that it is obvious, but nevertheless, let's explain this in more detail. This is some explanation. So assume again that you have some Lie group which is connected, real or complex, no matter, and G is Lie algebra of this group, and you have some finite dimensional, it's important here, finite dimensional vector space over the same field, R on C, and assume that you are given a representation of our group on this space, or linear action, this is the same. So this is a homomorphism of Lie group, of real Lie groups or complex Lie groups. This is real, and this is real, this is complex, and this is also complex. So we assume that we are given this representation, but then we have a derived representation of the Lie algebra on the same space. And because the group is connected, this is some exercise, easy exercise in Lie groups, Lie algebra, then the invariants for the group are the same as the invariants of the algebra. But what are invariants? What happens? I don't understand. What are the invariants? The invariants of the group, it's easy to understand. This is obvious. The vectors which are fixed by all elements of a group. But for the Lie algebra, the same condition means that these are vectors which are killed by arbitrary elements of Lie algebra. Now we apply this argument in our situation for the symmetric algebra and the universal envelope algebra. But here the situation is a bit different because these objects are not finite dimensional. But it's not important. But we can restrict our attention to finite dimensional spaces, the member of the filtrations, of a canonical filtration, because this is a graded algebra, and so it is in particular filtered algebra, and this is also a filtered algebra. And the symmetrization map maps this subspace to isomorphically to this subspace. And they are both, this is important, they are both invariant. They are invariant with respect to the action. I wrote here not invariant but stable, but this is the same. So we can restrict to these finite dimensional subspaces and apply the same argument. And then we get that we have a linear isomorphism between this object, the invariance, the G invariant in the symmetric algebra, the G invariant in this algebra, but these are sorry. But this object is exactly the center. So we get a linear isomorphism between invariance here and the center of our algebra. So this is a simple but important result, a corollary. Suppose that we know that the invariants on the left are generated by some homogeneous elements we found. We produce some homogeneous elements. Then the images under the symmetrization map are also generators of the center. So if you have generators of homogeneous generators of this, we can produce generators of a center. Moreover, if you know, if it happens that our generators on the left in the symmetric algebra are algebraically independent, then so are their images. So this is a simple argument to verify this fact using simple manipulation with filtration and the grading. So it's easy. How to apply this? Now, we want to apply these arguments to this, to some information, to getting some information about the center of our model example, the GLN Lie algebra. And we want to prove the following result, that without the center, this is not the center of the Lie algebra. This is by definition the center of a universal enveloping algebra. This is my notation for the center in the universal enveloping algebra. So the claim is that the center is isomorphic as an abstract commutative algebra to the algebra of polynomials in n variables. So in principle, we can find n algebraically independent central elements. Here we generate the whole algebra. How to prove this? So the idea is to prove a similar claim, but for the symmetric algebra. So the first lemma is some fact, some necessary fact about symmetric polynomials. So what we want to have, that the algebra, this is my notation for the algebra of symmetric polynomials in n letters. And the claim it is freely generated as a commutative algebra, which means that the generators are algebraically independent. I will use this term, freely generated, as a commutative algebra by the elementary symmetric polynomials, but also by complete homogeneous symmetric polynomials up to degree n, and as well as by power sum symmetric polynomials, also up to degree. How to prove this? We prove. So step one. So I recall the relations between the generating series in the whole algebra of symmetric functions. So we have three generating series for the elementary, for the complete homogeneous, for the power sums. And we know the relations between these three generating series. They are as follows. These two series are almost inverse to each other up to changing the sign. And H is the exponent x of P, the generating series for the power sums, or equivalently, P is equal to log of H of T, or almost the same for the E of minus T minus. And it follows from this equality of formal power series, one can deduce that for any two systems of generators, so A and B can be any, say A is P and B is E or B is H. This is just a notation for to explain that we take any, we pick any generating series from our triple. And then we have a following, that the element number n can be expressed through the elements of degree less or equal to n. And this means that we can pass from one system of generators to another system of generators. And the same holds in the quotient ring, the algebra of symmetric polynomials in n variables. And this entails that the three claims which are related to these elements, to these generators, and to these generators are equivalent to each other. If you prove something about one system, that you have a similar claim for another system. But now it's more convenient for us to prove our claim with respect to the elementary symmetric polynomials, but this is a well-known fact that the algebra of symmetric polynomials in n variables is freely generated by the first n elementary symmetric polynomials. But in this case, we also know that there are exactly capital N elementary symmetric polynomials. So this is a claim from, I think, elementary algebra. It can be proved. If you forgot how to prove it, just take it as an exercise. It is easily proved using induction on the number of variables. Okay, so what next? Let's take the space of all n by n complex matrices. Our group GLN operates on this matrix space but by conjugation. And take the algebra of polynomials, polynomial functions on this matrix space. And this is the most convenient way to deal with invariance. So we want to examine the invariance in this algebra, in the algebra of polynomials. So our group GLN acts here, and by change of variables, it operates on the algebra of polynomials, and we are interested in the invariance of this action. This is a typical problem of invariant theory. We have some algebra, and we want to understand the invariance in this algebra with respect to some automorphism group. In our situation, this automorphism group comes from the action of the group on the ground space. So we have a following lemma. The algebra of invariance is freely generated as a commutative algebra. All this means by the polynomials, which are the following. We take the power of a matrix, and take the trace, and take first n elements of this type, first n polynomials. And the claim it is that this gives us a system of algebraically independent generators of the subalgebra of invariance in this polynomial ring. How to prove this? Very easy. The first step is as follows. We just remark that these are indeed polynomial functions. So this is easy. The next step is that they are invariant. This is also easy. So the polynomiality is obvious, and invariance comes from holds because we have this property. So this is also trivial. Okay, so we have produced indeed some invariance. The next observation is that if we have some element which is invariant polynomial, then it is uniquely determined by its restriction to the subspace of diagonal matrices here. Why? But this holds because we are over the complex field, and almost every matrix over the complex numbers can be reduced by conjugation to the diagonal form. And the rest has, okay, it's enough to say that it is dense. This set of diagonalizable elements is dense. It is dense in the usual topology. It is dense in the Zariski topology. It does not matter. So for the polynomials, any invariant polynomial is uniquely determined by its restriction to the diagonal matrices. Next step? So we restrict it to the diagonal matrix, and we remark that it is a symmetric polynomial in this variable, so it's obvious. But next, that if you take our polynomial function and evaluate it on a diagonal matrix, we get exactly this expression. So this is the end of our argument. So we know that we already produced some system of free generators of the algebra for the algebra of invariant polynomials. But let's turn this into the claim that we need. So we return to our Lie algebra GLN. And this is my notation I will use with script letters for some reason, which will clear a bit later. These are the matrix units. So this is the basis in this space, which is formed by the matrix unit 1 on the intersection of a row number I and the column number J. All the remaining positions are occupied by zeros. So this is a basis. Next, some attention is needed here. What is done here? We consider at first glance formally. Take a matrix which composed from this matrix unit. So we place this matrix unit into this matrix. So this is, one can say this is a matrix composed from matrices, but it's not so terrible. Formally, it can be defined as an element of the algebra of matrices with coefficients in the algebra of symmetric of this algebra. We have the right to produce the algebra of matrices with arbitrary coefficients, commutative or non-commutative. This makes sense. So, and this is the equivalent formulation, reformulation. This object is the same as the tensor product of our ground field of the algebra, which is the coefficients here, and the algebra of matrices. So this is correctly defined. This object is correctly defined. Next, let's take the trace of the power number k of this element. So again, here all is correctly defined. This is an element of some algebra. We can take, we can raise it to power k. We get some matrix, formally an element of this object. Take the formal trace, the sum of diagonal entries. And what we get from this definition, we see that what we get is this sum, this multiple sum, k-fold sum of this type, E1, E2, I2, I3, and in the end, IK, I1. So we return this index return to the initial position. And we take the sum over all possible values. And what we get? We get some elements of this algebra, which are this Z sub k, our definition. Maybe any questions about this definition? Is it clear? Okay, no questions. Okay. So, for instance, the first element is just the trace of E, so the sum of diagonal matrix units. Z2 is the sum of such a type, and so on. The next lemma is follows. All these elements are invariants in the symmetric algebra. And if you take the first n elements, then we get the three generators of the subalgebra of invariance. How to prove? We just reduce this claim to the previous one about the invariance in the algebra of polynomials. So how to do this? More formally, we equip our Lie algebra with the inner product. Sorry, what is it here? I'm sorry. We take the inner product, this one, the trace of x multiplied by y transposed. This is my definition for the transposition. Why I need this operation? Sometimes people like to deal with x and y without transposition. And this gives us exactly the killing form, the invariant form on this Lie algebra. But here it's more convenient to introduce the transposition. And under this definition, we get that our elements are just an orthonormal basis with respect to this inner product. So the product of two elements is 0 or 1, depending on the fact if the indices are the same or not. And once we have an inner product on a finite dimensional space, we can identify our space with the dual space by means of our inner product. And when we can identify it's convenient, we can identify with Lie algebra and the dual space with the linear space of matrices. And then we can identify the symmetric algebra with the polynomials on this space. But attention, attention. We also need the action of our group. And with respect to our definition, the actions here and the action here are not the same. They are a little bit different. Namely, so here I wrote that under this identification, these matrix units, which are elements of this algebra on the left, correspond to linear functions. So special, the simplest versions of polynomials, which are, these linear functions are just the entries. The ij element is just the function which assigns to element y from here, it's ij entries. But I return to my claim. Okay, so a little bit, I will repeat it. So the elements, these elements, correspond to these elements, these polynomial functions, because the rule of forming these elements just coincides with the rule which comes from this definition. But this is my remark that I started and interrupted by. I would like to return to it. The identification map that just constructed, identification between this object and this object, commutes with the actions of the GLN, but they are slightly different. They differ from each other by the exterior automorphism, this one of this group. If one action on the left is this one, then the action which comes here, which appears here, is slightly modified. We have to use this automorphism in order to get this identification. But this is not important because the orbits are the same, so the invariance here, which corresponds to this action or to this action, are the same. So we can apply our argument and conclude that these elements are indeed invariants, and the first n elements produce a algebraically independent system of generators of a subalgebra of invariance in the symmetric algebra. So the elements, so I repeat again. So what we have proved? We have proved that these elements are free generators, of the symmetric algebra, of the subalgebra of invariance. Now I return to the proof of our theorem. We are interested in the center. So we note that these elements are homogeneous, and the degree is equal to k. And we obtain, if you take the images of these elements, which are in the universal enveloping algebra, then we get central elements by the Gelfand theorem, because the symmetrization maps invariants to invariants. So we get central elements. And the first n elements with indices from 1 to n just give us free generators of a center. So we conclude that the center is a commutative, is isomorphic to the algebra of polynomials in n variables. So just look again what we obtained from this argument. Our tool is the symmetrization map, which gives us some correspondence between the commutative algebra and non-commutative algebra. But the key fact is that this symmetrization map has good properties, and it is equivalent with respect to the action of our symmetry group. And this enables us to prove that the invariants on the left, on the right are the same, and this gives us the possibility to extract some non-trivial result about the center. Okay, so I would like now to explain, I have still some time, I would like to explain why we are interested in the center. So why the center? Why the center? The idea is, let's return to our main topic, representations. So we are interested, so we can assume that G is a complex Lie group, complex classical group. Classical is not important, but we are dealing with classical group. And we are interested in representations, so we consider some T, which is a holomorphic representation of G. And then it produces the derived representation dt, but I will denote also by T, derived representation of Lie algebra of our group on the same space. On the same space. So assume that T is irreducible. No, maybe it's better to sorry. So we have a representation. We have a representation, again denoted by T of the Lie algebra. Lie algebra. So G T is a representation of our Lie algebra. V is now our representation space. But now? This just means that this is a Lie algebra morphism from this Lie algebra to this Lie algebra. The Lie structure here is produced by the associative algebra structure by the universality property property, we get a representation also defined, also denoted by T, but of universal envelope. So we have now an algebra morphism, an associative algebra morphism or representation on the same space. Okay. But now assume that T is irreducible, and assume also that G is connected. Then T is also irreducible as a Lie algebra representation. And then it is an irreducible, for theory it is an irreducible representation of U of G. But you have a center, and by the Schur lemma, elements of a center are mapped to scalars. So for any element of a center, we have that the corresponding operator is a scalar operator. So the conclusion is as follows: an irreducible representation of connected group, Lie group G, gives rise to a homomorphism of a center to C. In our case, in particular, for G, L, and C, we get for irreducible T a homomorphism of Z, which is isomorphic to polynomial. Let me maybe write algebra of polynomials in n variables. We get a homomorphism of this algebra, to C. So now we want to understand. We know what are the irreducible representations. So we know that the irreducible representations are which corresponds to signatures. So we want to understand, given a signature, what is this homomorphism, which is called the central character of Z. It's a general construction. Central, no, sorry, it's not. I'm sorry, it's not central. It's not called infinitesimal. I forgot. Excuse me. Infinitesimal character of a center. So we want to compute it precisely. So the problem now, I will discuss it in the next lecture, is as follows. We have a center, in particular in the case of GLN. We know its structure, but we want to produce explicitly some generators in this algebra, and given a signature, so given an irreducible representation, we want to find this. It's not a good notation. Phi lambda to C. In particular, we want to find an explicit formula given the generator. We want to compute its image under this homomorphism. So this is the topic which I would like to discuss. So it turns out that for this problem, the generators which are given by the symmetrization map are not convenient. It's difficult to compute the image under the infinitesimal character. But it turns out that some miracle happens. We can just imitate the same construction that I recall this construction. Our construction was formally, it is the center, the trace of which is the sum of But now one can apply exactly the same construction to get directly central elements in the universal algebra as follows. See, use this one and define then exactly as follows. Which means that we say we take the same elements as here, same elements as here, but we consider them as elements of a universal enveloping algebra. So we write the same, just the same expression. But the product is in the non-commutative algebra. The sum is the effect is as follows. First, when these elements are in the center, second, there exists a nice explicit formula for this quantity. And the next time I will explain how to prove these two claims. Okay, so this is the end. Now we can discuss